don't hesitate to ask. So chapter 11, what we're going to do is look at roadway, or you might think of it roadway. Primarily, it would be roadway, yes. And we're going to look at roadway alignments, and there's two types of alignments. We'll talk about the horizontal and the vertical. So we're going to concentrate on horizontal alignment issues today, and then this lab will be dealing with horizontal alignments. And then on next week, we'll be following that up with vertical profiling, and then talk about vertical alignment. So there's three kind of things that go in and create a roadway alignment: the horizontal alignment, the vertical alignment, and then what's called a cross section. So one of the things we're going to talk about is those three-dimensional guys that we talked about a couple weeks ago with profiles and sewers and all of that. So you're going to kind of see that again. Then we're going to talk about station offset, and then I'm going to get into circular curve, data, and equations, and then talk about layout. In your book, you should be reading out of chapter 16, the pages that are listed here, okay? And then there's going to be some problems that we have. And there's the lecture handouts here. Hopefully you have these already published or printed out rather, have them accessible to look at. I want to look at some of these here and maybe look at these plan and profile sheets. I've got some sample problems here that I'll post probably by Friday. And then there's some other supplemental material that I might get posted for you as well. Then here's the lecture handout or the lab handout, and you could go ahead and print that out if you wanted for Thursday. I'll probably have a copy for you as well, but it would be good if you could read through that before we go out and actually do this lab, because this one actually is probably one of the more involved ones that we'll do, just because there's a lot of things to it. It's actually fairly easy to do once you get the process, but you're going to be laying out a circular curve or an arc, and that's always really tricky to kind of understand when you're out there in the field what you're actually doing. So that's what we'll be going over. So I'm going to go ahead and get started on the lecture material. If you have this open, this would be your lecture material. You could follow along. These are your your PDF files. So I'm going to go ahead and open my PowerPoint, and we'll start from here. Okay, so as we said, we're going to talk about alignment concepts as associated with roadways. Okay, and again, there's two types of alignments. Primarily, you deal with vertical and horizontal. We're going to concentrate, actually, just exclusively look at horizontal today, horizontal alignment. We'll look at coordinates associated with roadways. We've talked about these before. Those are not a big deal, but they're a bit different than the kind of coordinates that you're used to. So we have to look at those as well. We'll be looking at a little bit about plan reading. The one thing about plans, when you look at plans in a highway, it truly looks like spaghetti. There's just so many lines and arcs and curves and labels. So weeding out what you're really looking at and what you need, that's a big deal. Obviously, I don't expect us to be able to do that, but a layout person that does this kind of stuff, really, they're, that's what they're dealt with or dealing with. So we're going to concentrate on horizontal curves today, and then vertical curves next week. Okay, so that's where we're headed. All right, so when we talk about roadway locations, just like any other layout that we talk about, you're providing basically what's called line and grade. Now, you might also be talking about what's called cross-section, because at a roadway, every certain interval, you're going to stake out information, and that's based on your cross-section information. And they usually do that at every 50 feet or every 25 feet. So you need to think about that. If you're putting in a stake on a highway every 25 feet left and right of that center line for, let's say, miles of road, that's a lot of stakes. So there's a big thing going on there when you get into that. Most people, when they do curb, do it at every 25 feet. Sometimes if you're just doing pavement without curb, you can get by with every 50 feet. So line is providing, as we've talked about before, when we talk about that, that's in the horizontal plane, and you're giving it a northing and easting location, or an X and Y. And in highways, they almost exclusively use the concept of station offset. Now, the reality is that when you're talking about doing layout, you're probably using coordinates. So somebody has to convert northing and east, or station and offset information to northing and easting, or vice versa. So that's usually done in an office setting, not so much out in the field. And all of this exists in what's called your plan view. So in this case, all your distances and all your angles are horizontal. So this is an example of a very simplistic horizontal alignment. And what you're looking at is there's a baseline that is the magenta kind of color. That's got certain horizontal information. And then you actually have the alignment of the road itself, which is the red color. And associated with that are these things called stations. So you can see these little numbers. They're hard to read, but those are your station numbers. And then you've got curve data, which is associated with this curve right here, as we'll talk about what all that stuff means today. And then the green line would either be maybe your right of way, or it could be edge of pavement. It just depends. And in fact, you would probably see both on a real set of plans. So we'll take a look at a real set of plans here. This is just a CAD drawing, and I know it's rough to see, so this isn't a good example. But this would be all the stuff you see in plan view. So your stations, your coordinates, your curve information, your bearings and distances, this is all horizontal, okay? So then we have the providing grade when you're doing layout, and of course that's in a vertical plane, and basically you're giving them either a station and an elevation at that station, or a grade and a slope. And sometimes I refer to this as slope staking, where you're giving them slope information so that they know how to cut it up or down. That's really important when you get into ditches and those kind of things. We're not going to get that involved, okay, just so you know. And this is occurring in the profile. Well, actually, I guess I should take that back. In the profile, this is what's following the center line. I kind of got ahead of myself when I was talking about slope stakes. Those are typically in the cross-sectional view. So the profile is basically a graph that relates centerline stationing and elevation data. So we did see this in terms of the sewers. We looked at profiles where we had the inverts and the slopes on the pipe and those kind of things. We've got the same stuff going on in a highway. It's just a lot more involved. So this would be a very simple example of a roadway profile. And at the bottom, those green numbers, those are your stations of that roadway. And again, that represents 100 horizontal feet from 100, 1 plus 0, 0 to 2 plus 0, 0. The numbers over here, 820, it looks like 840, 860, it's hard to read those, but those are elevation planes. Okay, so that's no different than we saw on the sewers, but what we do see, a green line here is our existing ground line along that alignment, and the blue lines here, these are representing the actual center line elevation values of that alignment or that profile. And then of course you see in the cyan color blue, we see information that's relating to the profile itself. Okay, so we see like slopes, but we also see information here. This is called vertical curve. This is actually a parabola. So we'll see that parabola, we're going to go over that kind of stuff next week. And down here, we have elevations that are correlating to the station. So for instance, at station 1, the green number is the existing ground elevation, and the cyan number is the proposed elevation. So we get a lot more information on this than we do on a sewer. And again, we'll take a look at a real profile here in a minute. So the other type thing that you have to deal with is a cross section. And I am going to talk about cross sections next week a lot more. So this is another vertical plane, but this is dealing with a station and an offset and an elevation. And these are governed by a document called a typical section. And it's a cross-sectional view, just basically a graph relating what happens from the left of the center line and the right of the center line. And it gives you elevation and it gives you slope data. And if we look at it, this is a typical example of a typical section that would be in like say a subdivision road. So basically you see your curb datum. That line to the left is your center line. And you can see you've got a back a curb, then a sodded area, and then a sidewalk, and then you get out to this thing called the property line, and then it has slopes at 2-to-1 or 3-to-1. There's a whole lot of information along here, and this thing is happening at every point along that roadway. And in fact, when you get into roadway design, you may have 20 different typical sections because what's happening left or right of the center line is not always the same. So this gets really, really involved. And again, we're going to keep it simple, so we're not going to have to worry about all of this, but we are going to look at typical sections, and we'll do that next week a lot more, okay? All right, so we have talked about the different types of coordinates, either ground coordinates, what you might consider terrestrial, geodetic, plane coordinates, and state plane. A lot of highways are in state plane coordinates. So what that means is that you're working down on a plane that is actually either below your existing ground surface or above it. So those things have to be projected down to the ground if you're really dealing with those kind of coordinates. So you have to really be careful if you're using that type of coordinate. You can't use them as if they're on the surface of the ground, because they're not. Again, we're not going to go talking about that too much, but I just want to mention that because some people just really don't use those correctly. So we talked about the two-dimensional and the three-dimensional. We've talked about this before, but primarily you're going to be dealing in with a highway or a roadway alignment. You're dealing with a three-dimensional coordinate, and it's typically going to be spec'd out as a Cartesian. So that would be in terms of northing, easting elevation, or it could be in X, Y, and Z. So it just kind of depends on what you're dealing with. Now, the highway plans themselves are typically using what I call a hybrid system. It's what they call a station, an offset, and an elevation. So it's kind of like an X, Y, and Z, but the station is the distance along the alignment, and the offset is the distance perpendicular left or right of that. So that's a little bit different way of looking at things when you see this. Let me see if I have an example here. Okay, so you've seen these before. This would be the three-dimensional Cartesian. So where we have some kind of origin down here in and where the three axes meet, and then you're at an X value and a Y value and a Z value. Okay, so this is what we use pretty exclusively in design software. But highways, they use the concept of this guy, where we're looking at station offset elevation. So you can see station axis, the offset axis, and the elevation axis. Now, when you get into highways, let me see what my next slide does. Okay, so I want to flip over to my whiteboard here a minute. Okay, so when we get to highways and we talk about stationing, it's a little bit trickier than just XYZ grids. So let me draw a real quick alignment here. So let's see. Get up. So if I have, well, hold on. Something bugged out on me again. It never fails. Okay, so if we have a typical alignment, straight line alignment, if you're doing like this, okay, this alignment has a starting point. So if we're starting at, let's say, right here, this is typically referred to as 0, 0. If this thing is 500 feet long, then the end point of this would be at 5 plus 0, 0. So that's how stations work. Also, there's a concept of it's running that direction. So what that means is this is left of that alignment and this is right of that alignment, because you stand at 0 and look towards 500. So that's how you orient left and right. Does everybody see how that works? Any questions? Okay, so if I have a point, let's say right here, and I want to get its station and its offset value, okay, what I have to do is drop a perpendicular from that point down to the station. So this is perpendicular angle here. Where that perpendicular line intersects my alignment, I measure this distance. So let's say that distance is 300, and 95.62 feet. So the station would then be described as 3 plus 95.62. Then I have to measure the distance from that point to that. Let's say that's 100 feet. So then we would be an offset of 100 feet left. Okay. So that's not too bad as long as you keep track of the fact that you have to drop a perpendicular from your point down to the alignment, right? Does everybody see that so far? The problem is with a highway is that highways don't run straight forever. What's going to happen on a highway?
It usually curves.
Yeah, it's definitely going to curve, right? So it's going to get to a point, and then it's going to come into a curve. Okay, so what happens on that curve? Well, here it's perpendicular, but when I get on that curve, if I got a point out here, let's say, how do I do a perpendicular? Well, on any type of curve, you'll have what's called a radius point. A radius point. So that's the point where the two radiuses meet, and that defines that. So this would be your radius, and that would be your radius. Everybody kosher with that? You see that? So when you want to know what the station is to this point, what you do is you construct a line from the point that you want down to the radius point, and that's referred to as a radial line. Okay, so this line is called radial. Oops, let's get that out of that mode. That's a radial line. So when you have that radial line, then what you do is where that intersects your curve, you measure the distance from there to there. What is that distance, straight or is it bent? It's bent. So what we have to do, we have to figure out this arc length. Okay. So there's a way you can calculate that arc length, but it's not real simple. So once I get the arc length and I know this distance, 500 feet, let's say, so I'm going to take this distance plus the arc length to get the actual offset. So let's say we measured that, or we calculated that arc length to be 262.11. So the station in this point then would be 500 plus 262. So that would give us 7 plus 62.11. And the offset would be the distance that we measure from the arc to the point along the radial line. So let's say that that was 50 feet. So then this would be 50 feet left. Okay. So you can see right now, this makes it a lot tougher when you're dealing with arcs. Okay. And as we said, any road that you have is going to go straight for a while, and then it's going to bend, and then it's going to go straight again, then it's going to bend. And so this stuff just continues along that alignment, and that makes it a little bit more involved. Okay. And what makes it a lot more involved if you're dealing with coordinates, you may have a grid that you're putting this stuff into. So if you're taking this type of coordinate here and you're converting it to either a northing and an easting or an X and a Y, that gets real involved as well. Okay. So hopefully you guys getting that, appreciating that, but we're going to work with this a little bit, but we don't have to deal with it too much. But just appreciate what's going on there. Okay. Any questions? Okay, so let's talk about stationing. I think we have stationing is just yet horizontal distance measured along that alignment. So that's just kind of what we were talking about. So when you see 0 plus 2563 was how you would read that. That's just 25.63 feet from wherever the beginning point is. So a station of 12 plus 7201 is 1,272.01 feet from the beginning. Okay, so that's kind of how we look at that. When you hear the term full station, a full station in the imperial system our system, the English system, is a full 100 feet. Now, again, and I'm kind of glossing over this, I guess I'm assuming that you understand that when I say horizontal distance, this is the distance in the horizontal plane. It's not the distance along the slope of the center line of the pavement. So remember now, we have to deal with that. We've been dealing with that a lot already. So, but when you shoot a distance with your total station, it's giving you a horizontal distance. This is what it's giving you, okay? We talk about half station, that's a 50 feet fully horizontal, and quarter station is 25. So we use these terms a lot, full, half, and quarter, when we're talking about highways, because that's very, very common, okay? When you talk about station difference, or the difference between stations, it's just literally subtracting one station from another. So if you want to know the distance from station 500 to station 13 plus 3180, you just subtract the two, and what you have, that distance would be 831.80 feet, okay? That should be pretty simple. Any questions on that? Okay. The offset distance is also a horizontal distance, and as we said, it's left or right from the alignment. Okay, left is typically considered negative, and right is considered positive, and that's pretty true. I wouldn't say universally, but I would say probably most people in the United States, that's the way we do it, and also most of the software that you would ever use, that's the way it does it as well. It's again measured perpendicular to your tangent line, or it's measured radial to a curve, okay, as we just explained. So that's all important. And of course, elevation is the distance above or below that vertical datum at that point. Now, that could be given to you from a centerline profile, which means you have to calculate it through the typical section or something else. So this can be a big deal to calculate too. Elevation can be, because they don't give you every elevation at every point typically. They just give you the station and offset, and you should know how to calculate it. So we're going to be talking a lot about that next week. So we're going to ignore elevation for today. Okay, we're going to sidestep that. All right, so this is a diagram showing you what I just showed you in the whiteboard. So hopefully this will help explain it. But what it's showing you is your stations are running along from the starting down in the lower left corner and kind of working towards the upper right here like that. Stations are increasing in that direction. The point there has a perpendicular offset of negative because it's left. When we hit this curve, we have a radial offset of positive and a perpendicular like that. So you can see this system bends, okay? It's not like a straight grid. I mean, there's good things about it and there's bad things about it. Okay? You just have to get used to it because that's the way highways do everything. All right, so if we had to convert, this can be a big deal, okay? We don't have time to deal with that too much because we've got other things we want to talk about. But if you had to do this, you can take your station and offsets and convert them to northing and eastings, or vice versa. The good news is that most people are going to do this in software and let the software do most of the work. But if you had to do this by hand, it's not real simple. Okay, and especially if you have a big alignment. But on a situation like this would be a real simple one because I have a 90-degree line. So this is due east right here, 90 degrees northeast. If this is 5,000, 5,000, can anybody tell me what this coordinate would be here for 2? Anybody, how you would calculate that? What would be the northing and easting for 2 based on what we're looking at that picture?
Since it's due east, the northing would stay the same. Oh wait, no, it wouldn't.
No, it wouldn't. Okay, you're on the right track, but you're thinking wrong.
So it would be, since it's a 50-foot offset, the northing would be minus 50.
Right, so that would give us what?
That would give us 4950.
Okay, and then what about the easting?
The easting, since it's due east, you would just add the station to the 5,000 point.
Yeah, assuming that this is what? Station.
Assuming that is 00.
Yeah, see, we don't know that by this picture, do we? Okay, so that if you didn't know that, you could be wrong because actually 00 could be, to the left of that. But yes, assuming that 00, okay, this would be 5,600 for the easting. And as you said, it would be what? What'd you say for?
It'd be easting would be 5600.
Yeah. Okay. And then the northing would be.
It'd be 4950.
Right. Okay. So that everybody understand what we're saying there? This is pretty simple. Okay. Because what makes this simple is that the grid line is parallel with this alignment line. Okay. Now, what happens if you go to a situation where it's not parallel? Then you got a lot of issues. Okay. All right. So let's take a look. I want to show you some things like plan view plans and profile view plans. Okay. So let me, I'm going to switch over to my Blackboard site, and you guys might want to also open up these drawings. I have out here under your lecture handouts, I have a, let's see, a roadway plan and profile sheet right there. Oh, that's the wrong one. Well, actually, this is kind of a good thing. We'll look at this real quick. Let's see, let me rotate, see if I can rotate that. Okay, I think I've shown you this, guys, before. Maybe not. But this is showing you the two versions of, actually, the three things we talked about. This is the horizontal plan view sheet, okay? This is the profile associated with this. So where we're seeing that's existing ground and that's proposed. And what we're looking at is a 3D model of the two put together. And actually the cross section would be these lines that are running this way across there. There's a bunch of little lines. Those would be your cross sections. So if you notice what's going on here, this is indicating there's a lot of fill right here, because you notice where we're coming like through a chasm. Okay, so that's why there's all this fill. And this is the profile itself, and this is the plan view. Now I do have, let me see, there should be some better sheets here. Yeah, that's not the one. All right, give me a sec. I'm going to open this up for, let's see. All right, so this is a real set of plans, okay, just to give you an idea. And it's a little hard to see some of this stuff, but this, by the way, will be available for you. It's not active right now, but it'll be available for you here in a bit. This right here is what's called the plan, and the bottom part is called the profile. So this is what highways use. They call it plan and profile sheets. What I really want to impress upon you is it looks like spaghetti. You can just see a gazillion pieces of lines, and there's arcs, and there's stations, and there's all kinds of stuff. But what you should notice here, for instance, here's the center line of the roadway. There's your station. You have edges of pavement. You have right-of-ways. All of this stuff is going on. Right below it, this is the profile associated with that. And that has existing information. It has gas mains on it. It has water lines. It has existing ground. It has proposed. As we look at this, this is an intersection detail. And look at that. That's way more involved. You can imagine if you don't know what you're looking at here, you really better not be laying any of this out. And I actually I did a lot of the layout on Tylersville Road. I don't think this is the section that I did, but if you're familiar with Tylersville and US 42, anybody knows where that intersection is. I did all of that intersection at one point. It's been years ago. So this is the plan. This is the profile for that intersection. Look how much information is in there. It's just a ton. And then this is another plan and profile sheet. Okay. These guys right here, these are called typical sections or cross-sectional views. And notice they're occurring at every 50 feet. So this one's at 294 plus 50. This one's at 29400 plus 00. So these are occurring every 50 feet. And what you're seeing is superimposes the proposed information atop the old information. And this is really complex because they had an old road bed surface here, and they're actually putting a new one on top of it. So you're seeing a lot of information. Plus, you also see utilities and those kind of things in here. So that makes it just an involved set of drawings. So hopefully you're getting an appreciation for this. I will I'll make this available to you guys here today. So you'll be able to open this up if you want to look at it. Okay.
These first two pages,
Yeah.
um, they're labeling the stations as just 292, 293 instead of it
Correct.
being 292
Right.
plus 00.
Yeah. Some people do that. And the reason is, Jake, because it just saves on the information. It's implied that everybody knows that's 293 plus 00.
Okay.
Yeah.
So it does
So
make it look more
yeah,
messy.
it's just if you put the plus 00 in there, you can see how it starts to crowd this picture even more. What happens? Oop, let me rotate that. If I if I can see, can you see what I'm talking about? How that really starts to crowd it?
Yeah, definitely. It'd be a lot more
Yeah.
information than you need.
I mean, there's way more already. We're starting to see a bunch of information. But now, if can you look down here and you see it says 294 plus 40, and then it says
Yeah.
43.9, right? So there you actually can know, you know that it's really a true value there. Okay, does that make sense?
Yeah, that makes sense.
That was a great observation because you really do see that. Now notice this one here that it says plus 37.5. Do you know what that's indicating?
That would be plus 37.5 off of the 294.
Correct. So
Station.
that's actually telling you that it's at station 294 plus 37.5. But again, they just do it that way because it's easier to write with all that other information on it. Because I mean, literally, it looks like spaghetti, right? There's just so much information on there. And, first couple of times I had to do this, it was like, wow, what am I even looking at? But you get, if you start doing this a lot, it's just like anything else, you get real used to what's going on down here. Okay.
It actually makes a lot more sense because they keep the 294 blank and then everything off of that
Yep.
reads just as plus and
Right.
then the
Right.
value sign.
Exactly. And, really, I think we talked about this before, but intersection exits and entrances are really just using this same concept. They do it with miles as opposed to feet. So this would be in feet. Now, if this was a metric set of plans, it'd basically be the same thing, but this would be metric distances. So that would be 100 meters as opposed to 100 feet. But that's, of course, that's another issue, and we're not going to talk about that. Okay. The thing we are going to look at is this stuff called curve data today. And notice there's a whole lot of it here. We're going to talk about curves and how to construct curves because that's our primary focus for this week. But notice there's pi, delta, degree of curve, radius, tangent, length of arc, external secant. There's a lot of stuff there that we'll get into. Okay. Anybody else questions on here? I see the question about this. I'll have these open for you today, so you'll be able to pop these down if you want to look at them. They're pretty neat. And this is a real set of plans actually. And then this would be the profile associated with it. So notice at 294 here, there's 294 that correlates with it, and you can determine what the proposed elevation is based on the elevation up here at 294. So this is the proposed elevation of the center line of the road at that station. So right there, that's that elevate. It looks like it's it looks like 667.28 if I'm reading that right. And down below it, you'll see this other one. That would be the existing ground at that point. So there's a lot of information on here. Plus, we're also seeing pipes. Not so many pipes on here, but those are existing pipes. And then when we get to this other one, there's both existing pipes and proposed. Can anybody tell me what's the difference between the existing and the proposed as you look at this? Here's pipes here, and there's a pipe there. Can you tell the difference right there and there?
They're running at different slopes, so one's going up, one's going down.
Well, that's not what I'm looking at, but yeah, they are on different slopes. I'll agree with you. But here's the main thing. Anything that's existing is dashed, and anything that's proposed is solid. So that's another thing that they'll do on highways or, these types of plans. So you can see that even says existing storm manhole. So you notice the manhole's dashed coming down into the pipe that's dashed. But this is a proposed catch basin, and they're going to bring a new line into that existing line. So what they're doing is they're tying existing into, or they're tying proposed into existing. That's a real common kind of thing. And I think if we look at this, is that the this intersection is so busy. I mean, it's so terribly busy. There's a lot going on there. And this profile right now, by the way, is the profile that's running through Tylersville. There would be another profile on this set of plans, which would be for State Route 747, which would essentially show you the same thing, but in a different view. Okay, everybody okay with that? Lots of station, all those, notice all the stations and the offsets and all of this stuff. This is everything that you deal with is that way. Okay. All right, so let's go back to our slides. Maybe I'll leave this up. We may come back to this. All right, let's see. So from current slide. Okay. So we're going to talk a lot more about the vertical location and in profile and typical section next week. So we want to focus in on plan view. So when we talk about roadways and we talk about plans, they're really associated with two major features. You have what are called tangents or straight lines, and you have curves. And tangents are just a straight line that has a direction, and it's usually given in terms of bearing and azimuth, or it might be in terms of, actually I should say, instead of direction, I really probably should say distance here. So the straight line is composed of distances and then direction, and the direction is in terms of either azimuth or bearing. And I don't know if you saw that on those plans, but I think they were all in bearings. So then you have, at some point, you're not going to be straight forever. So you're going to then have what are called curves. So these curves are typically referred to as horizontal curves because they exist in what plane? What am I saying when I say horizontal curve?
That would be in like plan view.
Okay, which is the horizontal plane, right? So yeah. These curves are projected into the horizontal plane, and your tangents are in the horizontal plane as well. So they also are called circular curves, and what that's telling you is that that curve is based on the geometry of a circle, okay? To just say horizontal curve doesn't define the geometry. It just says what plane it's in. But when you say circular curve, now you're saying it's based on the geometry of a circle. And then we're going to talk about that today. So the other kind of curves that you would have in highways would be either called compound curves and reverse curves, or spirals. So compounds and reverses get much more involved, and then spirals geometrically are probably your most involved type of curve. And in any highway you drive over around here, you're using circular curves for part of those highways and spirals for the other kind. We might have some compound curves, but we would probably never have reverse curves around here because they're just, they're not going to be utilized at the center line because they would be a problem from a velocity standpoint or dynamics of your vehicle. So the most common we would see are circular curves and spirals. So a spiral is a curve that has a very, very large radius. Basically, it starts with a radius of infinity, and it goes to a radius of, let's say, 500 feet. So an example of spirals is where you enter and exit a highway. Okay, those are typically those entrance and exit ramps where they're curved. On most highways, those are going to be spirals. And what that does is helps your vehicle dynamically negotiate that speed change from a higher speed to lower speed or vice versa. So we're not going to talk about spirals or compound curves, but we are going to talk about circulars. So this little diagram is showing you the three kinds that I talked about. The simple circular arc or simple circular curve, that's the one we're going to concentrate on. A compound curve is a way that engineers use to do it to emulate a spiral. So what we're kind of getting is a spiral by putting two curves together, okay? But notice the radius on the first curve is greater than the radius on the second curve. And then you could have another curve with a smaller radius and another curve with a smaller radius. So you don't see these as often, probably more on the edge of the road rather than being in the center of the road, okay? So I've had to lay this type of curve out before, and I've certainly laid out many, many circular curves. Reverse curves, you can see what's happening. This would not be a good curve. If you're traveling at 60 miles per hour and you hit that point of reverse curve, your vehicle is going to want to keep going this way, and you're either going to flip that vehicle or go off the road. So we don't see these kind of curves very much at the center line, but you will see them at the right of way and you will see them at the edge, okay? So we're going to only concentrate on this simple circular arc kind of concept. All right, everybody okay so far?
Yep.
Okay, good. Is it making sense?
Yeah, I'm starting to get it.
Okay. So when we look at a circular arc, and I can remember circular defines the geometry, but when I say horizontal, I'm defining the plane it's in. So you could theoretically call this a horizontal circular curve. A lot of people just use the term horizontal curve, and what they really are talking about is this circular. So that's kind of a bad thing to say, but we all do it. Everybody just calls them horizontal curves, but in reality, what we're really saying is it's a circular curve in a horizontal plane. So curves are just arcs, okay? And if you remember, you guys have all had AutoCAD, right? So you guys know if you draw a circle in AutoCAD, it's real simple. You just give it a radius, point, and a radius, and it goes. If you have to design or add an arc in AutoCAD, that's not so simple. In fact, they have all of these different options to draw an arc, and drawing it properly, usually that's the hard part. But for any circular curve or horizontal circular curve, there are 8 defining elements. And you really only need 2 to actually define it. But we're going to talk about these and work with some of these here in a bit. So if you have a calculator, you might want to pull it out so we can kind of look at this. But so we have what's called the central angle. It's referenced usually by the Greek uppercase delta. It's also in some jurisdictions they use the uppercase I. So around here in Hamilton County, you usually see on sets of plans, you see delta. But if you're up in Butler County, it used to be, when I did some work up there, they used I a lot. So that tends to be a regional thing. The radius is the distance from the radius point out to the curve. And that's usually a defining, the delta and the radius are usually 2 of the big defining features. Then we have tangent, which is T, LC long chord, length of arc L. Then they have this guy called degree of curve, middle ordinate, and E, which is referred to as your external secant. I just want to look at this real quick. Let me go back to, I didn't want to do that, but okay, if I look at this right here, and I want you to see this, notice this says centerline curve data, and it says for the curve of 747. So we're talking about this curve right here sweeping through here. So it has a delta of 232600. Notice that's in degrees, minutes, seconds. It has a degree of curve of 2 degrees, excuse me. And highway engineers like to use degree of curve. But what that actually defines essentially is the radius. I want you to see, look how large that radius is. That's over half a mile long, that radius. So that's a large radius. T, 594 feet. The length of arc is 1,171 feet. So that is the bent distance along this arc from where it starts to where it ends. And then you have what's called the external secant. And this E here relates to what's called superelevation. That's called banking. So you guys all know what I'm talking about with banking. So it kind of tilts to the left or it tilts to the right based on which way you're turning. And that helps you actually dynamically stay on the roadway. You also see banking a lot on highways, interstates in particular. So we're going to focus. Go ahead.
So the banking would be 0.04 RT, so 0.04 right turn?
No, what that means is it's banking to the right, and the 0.04 is a percent. So that means it's for every foot you go left or right of the center line, you are raising or lowering 0.01 feet, okay? So that's actually 4%. So that's called a cross slope. You see what I'm saying?
Yeah.
Okay. We're not going to worry about that, okay? But they do have that's called your super elevation rate. And that's the maximum rate that it occurs. So basically your roadway is at a 4% grade across it. That's pretty steep, actually. If you were sitting on a stoplight on a icy day and you were just sitting there, your car may actually just kind of scoot off or to the right, because at 4%, that's pretty steep. Okay, you kind of get the idea?
Yep.
Okay. All right. So let's go back. We're going to talk about these elements now, okay? So what I want to do here is I want to talk about these elements, and we'll kind of diagram them. So I do have out here, and I think this picture is available to you right now. So I don't have to make this active. But under your lecture notes here, there's this guy called circular curve elements, okay? So this diagram is showing you how all those interrelate into the curve, all right? So I'm going to draw this, but you might want to have this handy if you're printed out, or open this up on your week so you can see what's going on with this. So let me kind of draw this here. So, and I'll explain each piece as we get into it, okay? So what we have in any curve typically is you have a tangent that comes into that curve and a tangent that goes out of that curve, okay, just like that. And where they meet, this is called your PI. Oops, I gotta get it out of that mode. This is called your PI, which stands for point of intersection. So what that is that's a coordinate location, okay? Basically a station offset or northing and easting. So if this is your 0 point, okay, 0 plus 0, 0, you're traveling this way. This is called your back tangent, and coming out of it is called your forward tangent, okay? So when you introduce a curve, well, I'm going to try this. I don't know how good this will work. Let me see if I can get this to work. Yeah, it's not too good. Let me try that again. That's a little bit hard to do. That's even worse. Yeah, it's not too bad. All right, so envision that curve being tangent. And so it has a start point associated with it and an ending point associated with it. And so where it starts, right there, we call that the PC. That stands for point of curvature, okay? So that's this point. That's the point where you go from the tangent to the curve. Where the curve ends is called your PT, point of tangency. So these are related by stations, PC, PI, PT. So who can tell me, would the value of the PT be higher than the value of the PC or less than the value of the PC?
Wouldn't they be equal?
No, because if stations are running this way, okay,
Oh,
you're going to hit the PC from a station standpoint before you hit the PT.
yeah. So the PT would be higher, but the distance between them would be like symmetrical.
Correct. Very good. That's because this curve is what's referred to as a tangent curve. So what that means is that it's 90 degrees with respect to those two lines, and it's 90 degrees here, okay? So from the tangent and that radius, that's a 90-degree angle, and this is a 90-degree angle, okay? And that's why you've got symmetry going on there, Jake. If you don't have a tangent curve, which you can have for certain applications, then you don't have that symmetric thing going on there, okay? That's a really good observation. So this point is what we call the origin of the curve. Some people call it the radius point, okay? But that's kind of where that curve radius is being measured from. So R, the one feature R, is your radius. That would be the distance from the radius point to the PT, or the radius point to the PC, or the distance from the radius point to any point on that curve. So R is a constant, okay? And that's not true with all curves. A spiral doesn't have a constant radius. It has a changing radius constantly. Is everybody okay with that?
Yep.
Okay, so delta. Delta is what's called the central angle. This is how big or small your curve is essentially. So it would be the angle measured at the radius point from radius line to radius line. That's your delta, okay? So you can see as delta gets bigger, that curve gets bigger. As delta gets smaller, it gets smaller. If we come up here and measure this angle between the two tangents, this is also delta. So again, this is because of that symmetry that you pointed out to me, Jake, that we've got delta here and delta here. Okay, does everybody see that? So hypothetically, let me ask you, if I gave you the bearing on this tangent and the bearing on this tangent, could you tell me the delta angle of this curve?
Yes.
Yes, absolutely. You could subtract basically one bearing from another. So this is what we would call the central angle. Okay, so then we have the distance from the PC to the PT. You can measure that two ways. You can measure the bent distance, which is defined as L. That's your arc length. So that's the big distance. What would be another way to measure that distance? If you set up with a total station at the PEC and shot the distance to the PT, would that give you the arc length?
No, that will give you a horizontal distance.
Well, this is a horizontal distance too, by the way. Okay.
That would give you the chord length.
It would give you the chord length, right? This distance from here to here is called your chord. And in fact, that's called the long chord, okay? Because it is the longest chord that you would have in this arc. Because we could have another chord that would go from here to here, or another chord that would go from here to here. And in fact, when we do layout, that's exactly what we're going to do. We're going to do these guys, which are called short chords. That's how we'll lay it out. Okay, is everybody with me on that?
You wouldn't lay it out from the radial point?
You could, okay. I mean, that's a really good point, but okay, let's think about that Tylersville curve I just showed you. That was over a half a mile away.
Yeah, you'd have to walk quite a bit.
Well, do you even think you could see it at half a mile away?
Definitely not, especially if there's a curve in the natural elevation.
Well, yeah, especially in our country, right around here. In a half a mile, you're going to hit trees and houses and hillsides and all kinds of stuff, right? So the answer is no. You're probably not going to use this to do layout. Now, let's say your radius is only 50 feet. What about that case?
Yeah, then it'd be easier.
Yeah, exactly. And in fact, when we do intersections in a couple of weeks, we're going to be doing that from the radius point because it's going to be a snap. But when you have a long radius curve, yeah, you can't do that because usually if obstructions are like you said, I don't want to measure a half a mile every time I'm putting a point in on that curve. It would be a real time consuming process. Okay. Yeah,
would you use the total station, or could you just like stake the steel tape on the ground and then rotate it?
Explain what you mean by taking the tape and rotating it.
Like if you were to stake it, well, I guess that would be hard to get at the exact value every time. But if you were like to stake it in the ground and then pull it each time and then just walk along that curve.
I think you're kind of on the right track. We'll get to that point, okay? When I start to talk about layout, let me come back to that. Or you hang on to that thought, okay? Because
it's kind of inaccurate though.
Well, there's two kind of ways to lay it out. You can lay it out with what are called long chords and short chords, and I'm getting there. Okay, I'll get there in a minute. Okay. All right. So another defining parameter of your curve is the distance called t, and t is the distance from the PI to the PC. And since this curve is symmetric, it's the same here. So it would be the distance from the PI to the PT as well. So PI to PC, PI to P, that's called your tangent of your curve. And as you probably guessed, all of these guys are going to have equations that interrelate them. So we're going to be talking about these equations here in a sec. Okay? We good so far?
Yep.
Okay. So here's another one. This one is kind of a weird kind of thing, but it's what a lot of engineers use when they define a curve. They use something called degree of curve. degree of curve. And the other thing that's really hard about this, there's two definitions. One is based on an arc definition and the other one is based on a chord definition. So highway engineers use what's called degree of curve arc. Okay, so what this is if you have a curve like this and the arc length is 100 feet, the angle down here that subtends that is degree of curve. So degree of curve is the angle that would subtend a 100-foot length of arc. Now, that changes based on whatever your radius is, okay? So if your radius gets large, if your radius is a large radius, your degree of curve is inversely proportional to that. So if your degree of curve gets big, your radius gets small. Does everybody see what I'm saying?
Yep.
So let's go look at that Tylersville example that we just said. Does anybody remember what I said the degree of curve was on that for that over half-mile radius?
It was
2.
0.04.
It was 2 degrees, I think.
It was 2.
Oh,
It was 2 degrees, right? So that's a pretty small number, right? But if your radius was 50 feet, your degree of curve would be a lot bigger, like, you know, quite a bit bigger, okay? So highway guys like to use this guy. Surveyors, we like to use this because it's a lot more straightforward. The reality is they're kind of the same thing. The only thing is that the radius is a distance that defines this curve, and the degree of curve is an angle that defines it. But it's kind of, I like to think of degree of curve as being the radius in terms of an angle as opposed in terms of a distance, okay? And highways use, like I said, they use this guy called an arc definition. Railroads do it completely different. If you're in a railroad, they use a chord definition. So they say it's the angle that subtends 100-foot length of chord. Okay. And we're not going to mess with that. We don't need to know about that. Okay. Any questions on that? So let's see how this all interrelates. Let's see, but I got some, we'll come back to that. Let me, I just explained those guys. Let me, now there's a couple of other ones on here that I've got on here. We're not going to need them, but delta and R, those are your two major things, okay? Most people use those extensively. T, lone chord, length of arc, degree of curve. Then you have these other guys that are less useful, middle ordinate and the external secant. We don't even really need to look at those. When we talk about significant stations, we talk about the PI, PC, and PT, okay? So I explained that. So POC is just a point on curve. That's all that means. So that can literally be any point that's on your curve. So any point between the PC and the PT can be a POC. Also, we talk about on the tangents, we'll talk about a POT. That just means point on tangent. So again, that can be any point that is on the tangent in terms of a station, okay? So those are your critical points. So again, here's that picture that I just had, and there's your back tangent, forward tangent. There's your delta or I angle, delta or I down here. Notice our radius. There's your long chord. There's your L, that's your bent distance. Here's your PC, PI, PT. And this is showing you how degree of curve works. So degree of curve here, D, usually denoted D sub C, that is saying that it's 100 feet up here for a highway on the arc, okay? Also, I want you to notice if this angle up here and that angle is delta, this angle down here is also delta, okay? So let's take a look at some equations and show you this stuff is not hard to do. However, you kind of have to, you have to really work with that degree minute second concept a lot, okay? So I think I have, let me go back. Okay, here's your major equations. So for any curve, your tangent is going to be equal to your radius times the tangent of half of delta. So when you're using this equation, you have to be really careful. You have to take the delta angle and divide it by 2, and then take the tangent of that. That's not the same thing as taking the tangent of delta and dividing that number by 2. So be really careful. Your long chord is your 2 times your radius value times the sine of half of delta. So notice a lot of these equations, they use delta, okay? That's a pretty common thing. For the arc length, you have 2 equations you could use, really 3. You can use the mathematical relationship that they've taught you in math, delta pi r over 180. Or you can use this relationship if you have your degree of curve, you can take 100 times delta divided by degree of curve. For a highway, these 2 equations are exactly equal. For a railroad, they're not. So you have to really, really be careful. You also should recognize that the distance L is going to be the difference between the PC and the PT. I really have this reversed. It would probably be PT minus PC. If I subtract this right now, I'm going to get a negative number. So that doesn't really mean anything, but it would just be the absolute value of that. Is everybody okay with those equations? We're going to see how to use them here in a minute. Okay. So here's some other equations. Degree of curve. For an arc definition, there's your relationship. Your proportionality constant is 5729.578 divided by radius. That'll get you your degree of curve, or vice versa. If you know your degree of curve, you can get your radius by taking this number and dividing it by degree of curve. Okay. So if you are dealing with external secants or middle ordinates, there's your equations, but we're not going to mess with them. But I do want to run through an example here with you. Okay, I don't know if I have one. Oh yeah, here's a sample problem. So here's a given curve. Okay, so we are given information about this curve, and we know that delta is 16 degrees and 42 minutes. The PI is at station 25 plus 6340, and the R is at 1000. So what we want to do is come up for the T, the L, the tangent, the long chord, the length of arc, the degree of curve, and the PC and the PT stations. Okay, so let's flip this over to my whiteboard, and we'll run through some math with this. Show you. It's not significantly hard, but the thing is, you have to just think about what you're doing here. Okay, so let's go to the taskbar here. All right, so I'm gonna clean this screen up, and we're gonna start a problem here. So I like to draw a picture, just kind of relates what I know. It doesn't have to be the exact picture of what we're looking at. It's just a picture that kind of, again, it relates what we're looking at here. So I know I have basically a tangent in, and I know I have a tangent out, and I know I have a curve somewhere like this, okay? And we're gonna call that and that our PC and PT. This is my PI. And what I just told you was that PI was told to you on this problem that this is 25 plus 6340. So I could assume that this is the PC or the PC here, so it doesn't matter. I'm just going to say this is my PC, okay? And this is my PT. So I don't know that. I need to calculate those. The other piece of information that was given to me was, let's see, radius. So we know the radius of this curve is 1,000 feet. And that's pretty typical curve in a lot of situations. Just to tell you, kind of give you an example, if you guys live in a subdivision and you got curves in that subdivision, those curves are probably 100, 200 feet long. But if you're out on a highway, they're going to be a lot bigger. Okay, because the size of the curve is somewhat related to the velocity, which kind of should make sense. So the other thing we know is delta. So we know that this angle right here was given, and this is delta, and this is 16 degrees and 42 minutes. Okay, so we need to solve T. We need to solve L. We also need the long chord. Those were all asked, okay? And then ultimately, I think they also wanted degree of curve, okay? So We can't do anything with stations until we have some of these other parameters. So we probably want to solve T, L, long chord, and degree of curve before we do stations. So since I have delta and radius, I can really start at any point. So I'm going to go ahead and do the T first. And T is equal to the radius times the tangent of delta over 2. So when I plug those numbers in, R is 1,000 times the tangent of 16 degrees and 42 minutes divided by 2. So remember what I said, you've got to divide the angle and then take the tangent of the divided angle, not divide the angle, tangent by 2. So let's see what we come up with. I'm going to calculate mine, and then you guys let me know what you come up with. I have my number. Anybody get a number?
146.776.
Okay, 146.776, you said?
Yes.
7, okay. And normally you would round that to 2 decimal places, so we could probably just call this 8. You agree? Right?
Yes. Yeah.
Okay. So that's perfect. That's what we should be getting. So that's the distance that we would measure back from the PI to the PC, or from the PI to the PT. So if we were laying out this curve in the field, we might need that number because we may have the PI and the back tangent location, but we don't know where the curve starts or stops. So this would be the number that we could use to lay that out with. Okay, is everybody good with that? All right, so the next thing we're going to do is calculate the long chord. So the long chord is the distance straight shot from PC to PT. That's defined as, whoops, 2R. That's defined as 2 times R times the sine of half of delta. So that gives me 2 times 1,000 times the sine of half of delta, which is 16 degrees, 42 minutes. Okay, and let's see what we come up with here. If anybody's not getting any of these numbers, let me know, okay? This is your long chord. If you, I got 290.44 feet. Anybody agree with that number?
Yes.
Okay, perfect. All right, so let's calculate the length of arc. So length of arc, L, is equal to delta pi r over 180. So delta is 1642. Pi, don't use 3.14 as the number because that'll round it too much. So make sure you're using probably what your calculator has is a much better number of that expression. Okay, so let's see what we come up with here. Okay. If anybody gets it, let me know.
I have 290.47.
291?
291.47, yeah.
All right. I'm glad you said 291. Although I don't think you did say it, did you? All
No,
right.
I didn't say it right the first time.
Yeah, but you had that, right?
Yes.
What do you notice? What do we notice? Between the long chord and the short and the length of arc, what do we see?
Very, very close.
Well, they're close. But
Yeah.
what's happening? They're close. But what's happening? The length of arc is what?
It's always greater than the chord length.
It's always greater. Okay. it has to be always greater. Just think about it logically. If you have an arc and you're measuring that bend distance and you got a straight shot, you look at that. It has to be greater, because if this was a string that I put on there and then I let that string go straight, it's going to get longer than the cord. Okay. So,
yeah, so technically the long cord is the shortest distance.
correct. It's always the shorter of the two. Okay. Now, let me say this. As your radius would approach infinity, the difference between the length of arc and the long cord would be almost nothing. Okay. In fact, they would almost equal each other.
It'd be unmeasurable.
Right. And actually think of this. If your radius of a curve is infinity, you actually have a straight line. You no longer have a curve. Okay? So we wouldn't talk about that, but basically that's what's happening. So as the curve gets larger, the difference between these two gets less. Okay? So as your radius increases, these guys approach each other. But in our case, they're almost a foot off. They're actually greater than a foot off, okay? And that's important. We good with that? Always look at that when you do calculations, because if you grab the wrong one or you calculated the wrong, that will tell you whether you're doing it right or not. Okay, that helps. All right, let's do the degree of curve. So let's see the expression. This is a 1,000-foot radius. So I want you to show you, we had like 2,000 something on feet. We had a 2 degree of curve. So for 1,000 feet, we should have a larger angle. So let's see what we get. 5,057, 29.578. That's called the magic number in curves, divided by 1,000. Now, what this is going to give me is a decimal degree, so you'll have to convert that to a DMS, because that's usually on a set of planes, that's going to be expressed as a degree minute second. So 57, 29.578 divided by 1,000. I get 5 degrees, 43 minutes, and basically 46 seconds and some change. Okay. Is everybody getting that number?
Yes.
Okay, so this number is going to be really useful when we get into curve layout. But for what we're doing right here, it doesn't have a lot to do with anything, okay? All right, so we have this guy solved. We have that guy solved. We've solved that, and we've solved that. So now, how do we solve stations? So does anybody know how we could solve the PC? Just looking at that diagram, what would you think you could do to solve the PC? If your PI is at station 25 plus 6340, and we back it off by T, we should be able to get the PC station. So this, on a set of plans, it's typically, they're going to give you the PI station related to the PC if it's not on there. So we can say this, that the PC is equal to the PI station minus T. So in this case, we have 2563.40 minus T that we calculated, 146.78. And let's see what station we come up with there. So we have 2563.40 minus 146.78. And I got the wrong number. Let me try that again. Looks like I came up with 24 plus 1662. Does anybody agree with that?
Yes.
Okay.
Yeah.
So, okay, guys, now you think about this. How do we get the PT now?
Wouldn't they be equal?
You
No.
add it.
No, we can't. They're not equal, because if we're increasing stations from the PC to the PT, there's no way they're equal.
Oh, I keep
PI
thinking
plus
it's
the T
symmetrical.
Okay, so I just heard PI
plus.
plus T. What do you guys think? Anybody think that's right?
Yeah, I keep thinking it as it being
Yeah.
symmetrical.
Yeah,
So I
yeah,
don't think it
right.
as station as it is ascending.
Exactly. I know what you're doing, Jay, but it's not right. Okay, here's my question. PT, is it equal to PI plus T?
Yep.
Never, never. Because we are traveling from the tangent. Now we're traveling along the curve. So we're not going this way and this way with stationing. We're going this way with stationing.
So can you do PC plus the long chord?
Nope, because that would give you a bent distance from here to here. I'm sorry, a straight shot.
Oh, okay, got you.
So what do
So
we
you would
need to
just
do
use the
now?
L then.
One more solution, right?
PC plus the L.
Right. So the PT is always PC plus L. Don't ever do it any other way. So what we're going to do now is we're going to say, well, that's going to be equal to 24/16 plus 62. And we're going to add to that L, which this is this L, not the long chord, the length of arc, 291.47. And let's see what we come up with. Plus 291, oops, 291.47. What'd you guys get?
27 plus 08.09.
Yeah, that sounds good. Okay, so that's good. That's good, and now we're set. Okay, you guys see how that works? That's a little tricky until you get used to it. Okay, but we'll be working with this as we get into this more. Okay, any questions? Not too bad, is it? These equations are pretty straightforward. Tangent, long chord, length of arc, degree of curve, and then stationing equations. Okay.
How'd
Definitely
you get
drawing a picture
the
helps.
degree of
I heard two people talk, so one at a time.
Sorry, I was just saying I definitely agree that the picture helps.
Okay. Oh yeah, Earl. I always draw a little sketch. Doesn't have to be perfect. It's just enough to give you kind of what it relates, right? That's all it needs. Yeah. Okay. Somebody else had a comment or question?
how'd you get the degree of curve? How'd you get the 5729.5?
I'm not going to derive that. That just take it for granted. That's a constant. It's a constant like pi. Okay.
Okay.
We're not going to derive pi, right? There is a pretty easy way to derive this, but it really is just, okay, since you asked, I'll do it real quick. If you,
Oh, no, you're fine.
but really it's just, okay, if you have, the circumference of a circle is what?
2 pi.
2 pi?
And pi times diameter.
Or
Right.
2 pi r, right? 2 pi r is the same thing as pi times diameter, right? Is that correct?
Yeah.
Okay. So if you have a circle and the distance around it is 2 pi r, the angle on the inside would be an angle of what? 360 degrees, right?
Yeah.
So 2 pi r is to 360 as, let's see, 100 is to degree of curve. Can you solve that proportion? Degree of curve would be what? It would be 360 times 100 divided by 2 pi r. You see that?
Yeah, I see that.
All right, so take 360. 360 times 100 divided by 2 divided by pi, and guess what you get?
The degree of curve.
57.29.578. Yeah, that isn't actually the degree of curve. That's the constant. That's the proportionality constant between the two. Okay.
Okay. And then that is always divided by the radius when we're trying to get the degree of curve for us.
right? And if you want to get the radius and you have degree of curve, you just divide the number by degree of curve. Okay.
Yeah, you just do it the opposite.
Yeah, because yeah, right. Okay. Does that make sense?
Yeah, it does.
So that wasn't hard to derive. That was pretty simple. All right. So let's go back. So we just solved everything here. Okay. So that's good. All right. So let's talk about curve layout because this is what we're going to be doing in the lab. There's three methods really. You can use what's called a deflection angle long chord. You can use a deflection angle and short chord. You can use coordinates. Really, a fourth method would be the method that Jake suggested. Well, why don't we just occupy the radius point and do it that way? And we could do that, but if you have, as we said, if you have curves that are really, really big, that ain't gonna work, okay? So a lot of people out in the field now are using coordinates and radial stakeout, or they're using coordinates that have been downloaded to, let's say, a GPS controller, and they're doing it via GPS. But actually, deflection angles and short chords and long chords can be pretty quick. So that's what we're gonna use this method out in the field, okay? So I'm gonna show you some diagrams here. We'll run through the math. The math is really simple on this. So this diagram is showing you an example of using what are called long chords to lay this out. So you usually occupy your PC. You could occupy your PT, it really doesn't matter. But you could let's assume we're occupying the PT. You either backsite the PI or you backsite the tangent. The angle between the tangent line and the chord here, this is a short chord. Actually, they call these long chords. But the angle between this tangent and that chord is called the deflection angle. And then you would have the next deflection angle and the next deflection angle and the next deflection angle and the next deflection angle. These guys increment, okay? And there's a geometric relationship that's happening between these. And what's really cool about this, notice we have delta down here from the radius to the radius. For the last deflection angle, which is the deflection angle from the PC to the PT, it's always half of the central angle. So this angle right here is always going to be d over 2, but that's delta over 2. But these angles are going to increment differently, but they do increment geometrically. So there's a real simple equation to use to do these. Okay, I'll show you that here in a minute. So this is what's called a long chord method. They're referring to these as being long chords, but they're constantly changing. This is the long chord of the curve, but these are incrementally long chords. Does everybody get the idea? So we have to go ahead. Question?
Would it be like an exponential value?
Would what be exponential?
Like the relation of the PC to the point on the chord?
No, they're actually geometric. It's very geometric. So what we'll do is we'll be able to calculate this angle really easily. And once we know that angle, then we'll be able to calculate that chord really easily, okay? So the key thing is getting this angle, which we can refer to as a deflection angle. I use the symbology little d over 2. Some authors, and I think your author uses a little bit different nomenclature, so kind of watch it if you read the book. But I'll show you a method how to do it. So it's not really exponential, it's geometric, okay? If that makes sense, right? And this is the method we're going to use out in the field. Actually, we're going to do a short chord method. So let me show you that method here. So this is what's called a short chord method. So what you're doing here, and it's a little tricky on this diagram to see it, but the guys from that first point to that point is your short chord, and then the next point is the short chord, and the short chord, and the short chord. If the interval here is like, say, every 50 feet, these short chords are all the same. But the starting short chord and the ending long chord are not, or short chord rather. Now, the angle, you're still turning the same angle. So you turn the angle from the PC to that point and the angle to this. So you have those still deflection angles, but you're laying it out differently. This method is real nice if you're steel taping. And if you have 2 guys or 3 guys, one guy runs the instrument, one person holds the back sight, the back point, and then the other person measures it. Okay. The other method that we were just looking at, the long chord method, is real nice if you have a robotic total station or you have 2 people and if you had two people that were measuring, one guy using the rod, one person doing the instrument. Okay. So we're going to kind of use both methods on Thursday. So here's the equations that you need to calculate these deflection layouts. Any deflection angle on a curve is going to be equal to the length of arc times the degree of curve divided by 200. And degree of curve is a constant for the curve. 200 is a constant. And this little L here is just the difference between the stations. So that means where you're sitting and where you want to go. That's what that's saying. Okay. Any long chord is going to be equal to 2r times the sine of d over 2. And I usually use the term little c here for chord. Okay, I think I have a diagram here that shows you this. Let me go to the next slide. There it is. Okay, so what we're saying is, if I want to calculate that point right there, I can calculate that angle, the d over 2 angle, and then I can calculate this chord value c here. And what this is showing you is this angle here to that point is actually angle d. It's twice that. And this angle up here is always half. So Jake, there's your geometric relationship. The angle at the center is always half over here. So if I go to the next station, I would have an angle here, and that one's going to be half. Okay, and you're using this equation, 2r times the sine of that deflection angle to get this distance. So let's go ahead, let's look at another quick example here, and I'll show you how easy this is to do. This is real simple to do, and again, that's exactly what we're going to do in our lab on Thursday. So let's look at this curve here. I'm going to use this same curve. Let me just kill this diagram. I'm going to generate a new diagram. So we've already created all the data we need for this curve. Let me just draw a quick diagram here. So there's my point. I want to lay this curve out, okay? So this is looking at the PI right here, okay? That's my PI point, and this is my PC point. So we're assuming I'm sitting at the PC. We know on this curve that the R is 1,000. This is the same curve that we just did, by the way, okay? We know the degree of curve. What did we solve the degree of curve for that? It was 5 degrees and something. Anybody have that written down?
5, 43, 46.
Okay. We also know delta, which was what, 1642, right? And we know the station of the PT, we solved that to be what, 20, or PC, 24 plus 16.
62.
Okay, cool. So that's all we need. So we're going to set up a little chart, and we're going to say, I'm going to sit at a certain station. From that station, I'm going to go an L distance, and then I need to know what my degree of curve or my deflection angle is. This is called your deflection angle. I need to know that because that's what I'm going to turn out in the field to lay this out. And then I'm going to calculate a long chord. And if we have time, we probably won't, but I'll show you how to do a short chord. Okay. So we're sitting at the station PC, which is 24 plus 1662. And we're going to do this, let's say, every 100 feet. So the next station I would be 25, and then 26, and then on and on and on. Everybody get the idea? So I'm going to be here, station 25, and then station 26. And I could do this for every point along that curve until I get to, actually, I would have 27. And the last station point is 27 plus 0.809. Okay. So sitting here, there's nothing to do. So there's no length of arc, there's no deflection angle, there's nothing. But from here to here, there's going to be an angle and a distance. So what we need to know is the distance from here to here, okay? So how do we get that distance? How do we solve that distance?
You just subtract one from the other.
Yeah, so we got 25, 16.62 minus 2,500. What's that give us? Get 8380? Is that what you guys got?
Yep.
So the distance from 24 to 26 is going to be 183.80. And then from 24 to 27, 283.80. And then ultimately, this distance is going to be what we calculated for L, which should be 291.47. You guys get that?
Yep.
So to calculate this, here's all we do. We take L, multiply it by degree of curve, and divide it by 200. So what's cool about this equation is that degree of curve divided by 200 is the same for every one of these deflection angles. The only thing that's changing is what? This guy. You see that? So degree of curve divided by 200 is a constant for this curve. And so all I have to do is take degree of curve, divide it by 200, store that number, and multiply it by L, multiply that recall by L, multiply the recall by L. So each time I do that, it's just incrementing. So this equation does all of your work. So we're going to take 5 degrees, 43 minutes, and 46 seconds, and divide it by 200, and multiply that by the first number here, 8380. And see what you get. 5 degrees, and I didn't get it right because I did something wrong. It shouldn't be a very large number, by the way. The first one, anyway.
I got 2 degrees, 24 minutes, and 2 seconds.
Okay, hold on, you're probably right. I just didn't do mine right. Let me see what you get. If I agree with you. What'd you say?
2
degrees.
degrees, 24 minutes, 2 seconds.
Okay. And I agree. I agree with that. Okay. All right, so we're going to do that same thing again. Let's just keep doing that. And what we'll notice is those numbers are going to get bigger. Let's do that all the way to the end. And if you guys get them, let me know. I'll write them down. You guys can verify my numbers. Mm-hmm. Anybody get that?
That's what I got.
Okay, cool. Let's get the next one. It's not really hard. Pretty simple stuff. 8 degrees, 7 minutes, 48 seconds. So let's do the very last one. Eight degrees, 20 minutes, and 50 seconds. Are you guys agreeing with my numbers?
Yep.
Okay. So there's a geometric relationship here happening here, Jake. But one thing I want to point out is that, what do you notice about the last deflection angle? 8 degrees, 20 minutes. Anybody see a relationship between that and our initial curve? 8 degrees, 20 minutes, basically 8 degrees, 21. You could call it 8 degrees, 21. Does that make sense with anything? Look at your degree, look at your delta.
Oh, that's half a delta.
It's half a delta. It has to be half a delta, okay? If this number doesn't come back to half a delta, then you got a problem. So you always got to check, okay? And if this isn't exactly half a delta, why not? Anybody know why?
rounding
Where's the rounding occurred?
and the delta.
Nope. Delta was a pure number. It was given.
Oh yeah.
And the length.
How about this right here?
Uh,
Remember when we calculated that? That wasn't exactly 46 seconds. Okay. We rounded out that change. Okay. If you use that out with decimal seconds, this number would hit this guy exact. Okay. But for curve stakeout, this is fine. I don't even worry if it's a minute or two off. I usually don't worry about it because that can just be rounding. We okay on that? Let's do our long chord. So the long chord relationship is just 2 times the rate, or the chord. We'll just call it the chord. That's 2 times the sine of your d/2 angle, okay? Now, this angle's already divided by 2, so don't divide it by 2 again. You just plug that in directly and 2 times the radius. So let's see what we come up with. So that first long chord, I got 2 degrees, 24 minutes, and 2 seconds. I'm going to take the sine of that times 2,000. Guys, tell me what you get. It's like 83.77. Anybody get that number? I didn't get that number. Hold on a minute. I think that's wrong.
I got 83.77.
Okay. You know what, guys? I think we got a mistake. Anybody see the mistake?
Yeah, on your links, I think it's 83:38 instead of 80.
Yeah, I have a mistake here. You guys might want to check this in your notes. And that was my bad. I don't know why. That was my bad. These numbers should not be 80. They should be 38. So all of these are off slightly. Okay. I apologize for that. I just now caught that. This should be 83.38, 83.38, 183.38. So these are going to be off just a slight amount. Okay. But you guys get the idea, right? What we're doing here.
Yeah, that makes sense.
All right. So let me go back here quick because I know we got to get out of here soon. This is what we're going to be doing in the field. We're going to be laying this out, okay? And, oh man, I hate making mistakes like that. Whoa, what is that thing? I don't know what that, I don't know what that thing was. All right, so let's go to the lab real quick, okay? So I do have this lab available for you under lab handouts, okay? So you can read through this for Thursday's class. And I'll show you what we're going to be doing here on this picture. We are going to be laying out this little piece of roadway. So this is our control points, 104, 101, 102, 103. We're going to set up by radial stakeout some of the key points. So I'm going to have these tangent points here, PC points here, and PT points here, okay? So we're going to stake out 1, 2, 3, 4, 5, 6 points. I think we have 3 groups that we're going to run, so I'll have you guys set the center points as well. And then we're going to occupy the PC. We're going to put the tangent points in this way, and we're going to deflect around this curve into the PT. So I'm going to have one group that's going to do that on the inside side of the pavement, one group on the outside side of the pavement, and one group on the center line. Okay, so this is your curve that you're going to lay out. If you want, and this would be a good sample problem to do, see if you could calculate the deflections from the PC to the PT. There's your curve data right there, your length of arc, your radius, and your delta. You need that. And we're going to do it at a 25-foot interval. And hopefully you won't make a mistake like I just did. Wasn't a big mistake, but it was a little one. So that's what we're going to do. We're going to lay this guy out. We're going to lay out the left edge, the right edge, and the center line stakes. Okay, and I think we're going to have a good day, just a little bit cold on Thursday's class. The other piece of this lab, this is the profile. We'll be talking about that next week. This is kind of a three-dimensional model of what you're doing. It's looking at the PC, or we're sitting at the PC looking towards the PT. So this is the existing ground, and that's the proposed ground and what's going on. And then these guys are typical sections. Those are going to be important for next week. Okay, but we will be, let me explain this too, because the inside and the outside of the curb, they are going to be, your center line is here. We're going to be 14 feet off of that. And we're going to add another 3 feet for our offset stake. Okay, so we're actually going to be doing this at 17 feet. So we'll have to compensate for that. So I'm gonna calculate the flexion angles for you. I'll have those calculated, and that's what we're going to be bringing in on. That's what we're going to be doing on Thursday. So I think you'll like it. It's pretty cool once you see this curve come in. Okay. So download this and look it over. Read it for me, please, so you got an idea what we're going to be doing. I have some homework problems out here for you guys to tackle, and you don't need them for Thursday, but I would try to get them for next Tuesday. That would be helpful. I have some supplemental stuff here that I'm going to give you. I'll probably turn this on today. And there's a horizontal curve problem that you can run through. It's giving you the information, and it shows you how to do everything. So I'll have that out there. And that way, actually, it's the one we just went through. And then I think there's the layout pieces of that as well. So this will show you how to run through the layout. So I'll get this guy activated. This is the one that I just did on the board, but this one's not blown. This one's correct. So there's your different stations and everything. Okay. So does anybody have any questions before we get out of here? I'm going to stop the recording real quick.